In the first experiment, we are going to analyze the time response characteristics of first order system, second order system in open loop as well as in closed loop. First, let us start with an open loop system. We analyze the time response characteristics of the system, especially for step input. To create a transfer function, I have to use the command tf. I'm going to create a transfer function 1 divided by s plus 1. So I have to type like this, tf of open bracket within that numerator polynomial comma denominator polynomial. So in numerator I have 1 and denominator I have s plus 1. So I have typed 1 1 1 1 in the sense s plus 1. If you type three numbers 1 1 1, it means s square plus s plus 1. So based on the number of elements available in the row of a matrix, MATLAB automatically identifies the order of the polynomial. Okay. So if I press enter, we will get a transfer function object. In order to see the step response, we have one command, that is step of g. So once you have pressed enter, the step response will be plotted. In that, if you right click, there will be a menu called characteristics. You can choose different kinds of options like peak response, settling time, rise time, steady state, etc. You just click on settling time. Okay. And if you hover your mouse over it, over that particular point, it will display the settling time. Similarly, select peak response. I think for first order system there is no peak response. Let us select a steady state. So steady state value is here, and final value is equal to 1. This is one command. So the first task of the experiment is to analyze the effect of pole in a system in first order system. Let us create a system with a different time constant. Okay, the system I am going to consider is going to be k divided by tau s plus 1, in which k equal to 1. We are going to vary the value of tau or t and check what happens in the response. Let me put 2 seconds. Okay, before that, we once again note it down the response. The settling time is going to be 3.91 seconds, approximately 4 seconds. Okay, now I am going to create another transfer function with the time constant equal to 2. If I check the step response of the new system, you can find that the settling time will be exactly double that of for previous. Okay. So the first task is to analyze the variation in the pole of a system or time constant of a system, and we will observe what happens in the response. If the time constant is negative, that means our pole will be positive. Okay. At any time instant, we can check the poles and zeros of the system using the command zpk. If you pass zpk within the bracket your transfer function variable, and if you press enter, let me close this tab. Okay. So it displays the same system in pole zero form. Okay. The form, whatever it is displayed here, it is called time constant form. In the previous class, I have explained about it. And if you take the time constant as a common factor and if you move it to the numerator, then you will get pole zero form. So for the system, the pole is at minus 0.5. If you solve the denominator term equal, if you put denominator equal to 0 and get the solution of s, that is the pole of the system. Okay. Our objective is to analyze what happens when this pole of the system varies. So for that, we vary the time constant of the system. We create different types of objects, and we observe the transient response. Only 2 commands are there. Okay. Let us see the step response of the system. And if you have a negative time constant, then the system is not at all settling. Okay. I do not know whether you are able to see this value. The y-axis is in the magnitude of 10 power 25. Even there also it is exponentially rising in the negative direction. That means system is completely unstable. Okay. The pole position determines the stability of the system. Also, it determines the speed of response of the system. The first task you are going to do this. The second task is for analyzing the effect of zero. Okay. For that, we are going to consider a system with one pole and one zero. Rather than manually entering the number within the command, you can also create a variable. Okay, let me put t equal to 1, and let us create a transfer function g equal to tf of. I'm going to create a transfer function ps plus 1 divided by s plus 1. Let us check the step response. See here, there is no dynamics. Uh, Output exactly follows the input step pattern. Why? Because if you look into the transfer function, it is s plus 1 by s plus 1. Theoretically, the numerator and denominator will cancel each other. Hence, there is no dynamics. Let us change the value of t equal to minus 0.1. Let us observe the response. I have not created the transfer function. Sorry. Let's observe the response. Now, the system has a 0 at plus 10. And because of that, what happens is when a step input is applied, the response of the system will not start from 0. It will start from arbitrary variable. What it means is, whenever a step input is given for a very short interval of time, the response will move in opposite direction, and after that, it will move towards the direction of your input. Okay. Usually, such kind of systems are called non-minimum phase systems that we will see in the next experiment. Usually, control of such systems are very tricky. You just see here, zeroth amplitude is here, but the input is starting at some other point. Okay, let us put a different value of t and let us check it. Let t is equal to minus 0.1. Okay, that we have seen. Minus 0.5. Let us create a transfer function, evaluate the step response. Now we can see that when a step input is applied, step input in the sense, input is applied exactly at time t equal to 0, and the amplitude is going to be 1. When a step input is applied, you see that response is starting from some negative value. That means momentarily the response will be in the opposite direction of your input, and after that, system will converge to the final value. Let me put some positive value of t. I put 5. Create this transfer function, evaluate the step response. Now you see here, I have applied an unit input to the system. Okay, finally, the system is 1 by s plus 1. That is the dynamics part in the denominator. That is, the pole is at 1 and system gain is 1, and finally it is settling at 1. Okay, here it is settling at 1. But you see from where does it start? It is starting at 5. Okay, so the 0 of the system adds some amount of differential of your output, and it will affect the transient response of the system. but it will not affect the steady state. Okay, whatever may be the value of t you put in the numerator, you can see that finally it will settle at 1. But the starting point will arbitrarily vary. This is the effect of 0. So this is the second task in our experiment. The third task is we are going to create a second order system. In that, there are two factors, that is damping ratio and natural frequency of oscillation. First task in that, we will vary the damping ratio and observe what happens to the transient response. On the next task, we will keep damping ratio constant. We will vary the natural frequency of oscillation omega n, and we will observe what happens to the response. Okay. Let us create two variables. That zeta represents the actual damping ratio of zeta. Initially, let it be 0. And Wn, I am going to use as a symbol for natural frequency of oscillation omega n. Let it remain as 1. I'm going to create a typical second order transfer function g equal to df of omega n square divided by, in the denominator term you will have s square 2 zeta omega n s plus omega n square. Okay, these commands are available in the skeleton record. You can refer to it. Just to get a feel, I am doing everything once. Now let us see the step response of the system. You can see that the system will have sustained oscillation. That is why it looks like a band. Let me zoom in. System is completely oscillating. Okay. So this is the effect of damping ratio. If zeta slightly increases, system will be underdamped. As of now, if zeta equal to 0, such a system is called undamped system. It will completely oscillate. So a good example is an ideal LC tank circuit without any internal resistance. In such case, if you excite it and maintain the LC circuit, it will continuously oscillate at the frequency 1 by 2 pi root LC hertz. Let us change zeta. In MATLAB, if you press up button, the previous commands will be available. Let me set zeta equal to some 0.1 and let us create the transfer function, evaluate the step response. Here you can see it is an underdamped response. So for this response, you can find maximum peak overshoot. Select peak response, and if you hover your mouse over it, it will show the peak overshoot, and you can also see the settling time. So the third task in our experiment is to analyze the effect of variation in this damping ratio. If we put different values of zeta, let me put zeta equal to 1, and if we create the transfer function and see the step response, we'll have completely different effect. Okay. It is critically damped system, that is zeta equal to 1. It doesn't have any overshoot, and if you see the pole position is at pk of g, so it has two poles at exactly same point. See, you have the transfer function 1 by s plus 1 whole square. It is s equal to minus 1 minus 1. So whenever system is critically damped, two poles will be exactly at same position. So likewise, we can change the value of zeta for different values, and you can observe the response. Let me consider another zeta, zeta equal to 2. This is a over-damped system. Over-damped system in the sense the system will be very sluggish. It will look more or less like a first order kind of response. Okay. and it will take much time to settle when compared with the previous system. Will be very slow comparable. The next variation what we are going to see is to keep zeta constant. Let us keep zeta at some value 0.707. You can take any arbitrary value. I consider an underdamped case 0.0707, and omega n we are going to vary. Initially, let omega n, I think whatever we have plotted is for omega n equal to 1. Now let us check for omega n equal to 0.1. Create the transfer function. See this step. Here you can observe that whatever may be the value of omega n you put, the maximum peak overshoot will remain same, and only the settling time will vary. Not displayed. The settling time is 59.6 seconds. So let me put a different value of omega n. Instead of 1, I'll put 5. The zeta is remaining constant. Let's create the transfer function from this step response. Here also, you see that the shape of the waveform will remain almost same. It will not vary. Okay. But if you check the settling time, there will be variation. Why? Because zeta determines the maximum peak overshoot. Okay. If zeta remains same, the peak overshoot of the system will remain as it is. So there will be variation only in the settling time or time related parameters. Okay. Usually in time response, we consider rise time, okay, peak time, settling time, sometimes delay time also, but usually maximum peak overshoot and settling time are enough. So this is the fourth analysis, that is to analyze the variation of omega n in the time response. And fifth analysis, okay, rather than changing omega n and zeta independently, the second order system is going to have two poles. Okay. So we directly enter the pole position and let us observe what happens in the response. Okay. I am going to create two pole. The first pole is -1 plus 1i. I means complex number j. Okay. And second pole is going to be -1 minus 1i. The poles, if they are complex, they have to be complex conjugate. Okay, this we need to keep in mind while creating the pole. If we know the pole position, then the characteristic polynomial in the denominator is going to be s minus p1, s minus p2. Okay, that is polynomial multiplication. In MATLAB, you can do these kinds of polynomial multiplication. Further, there is a command called convolution, conv. In that, I am passing the variable 1 minus p1, 1 minus p2. Why 1 minus p1, 1 minus p2? Because if you have pole position p1 and p2, in the denominator of your transfer function, you will have factors like s minus p1, s minus p2, etc. Okay, so for that, we create a first order polynomial. S coefficient is 1 and the s power 0 term is minus 2. So this is the response. This is the denominator term. Let me assign it to some variable. Okay. Let us create a transfer function equal to tf of. Usually the second order transfer function standard pattern will be omega n square by s square plus 2 zeta omega n plus omega n square. So the last term in the denominator will be available in the top. So I put last term of denominator, then denominator. Let us see the response. Okay, so we are getting some response. Now what I'm going to do is I'm going to change the value of P1, P2. I will keep real part constant, but imaginary part I'm going to change. P1 is -1 plus 3i. P2 is going to be -1 -3. Initially it was -1 plus or minus 3. Now I am changing it to -1 plus or minus 3. Let us find the convolution, create the transfer function, and find the step response. Now you see the response is completely varied. Okay. This analysis, in this, we are going to keep the real part constant and we are going to change the imaginary part. The inference what you can get from this is, I'm not going to run everything. You just try it by yourself. I am just typing the sample cases. In this, what you can infer is, irrespective of variation in imaginary part, your settling time will always remain constant, but only your peak overshoot will vary. And similarly, the next task will be keeping the imaginary part constant and varying the real part. In that, you can observe that the real part determines the speed of response, and imaginary part usually it will be responsible for the oscillation profile in the transient response. So this is with regard to second order systems. So for third order system, not only for third order, even for higher order system, the textbook doesn't do much analysis. Why? Because in general, they introduce a word called a dominant pole approximation. What it does is, if you have more than second order, two number of poles, and provided that few poles are very slower and other poles are very faster in the dynamics, you can leave those poles and reduce the order of the system to either second order or first order. This idea is called dominant pole approximation. Okay. So for that, I am going to consider a third order system in which you have three factors in the denominator. It is a square plus 2 zeta omega n s plus omega n square, typical second order. Along with that, you also have a time constant term Ts plus 1. So let us create T is equal to 1. Okay. All these commands are available in the skeleton record. Okay. Just for reference, I am intentionally typing this. We also require zeta equal to 0.707. Omega n is equal to, let it be 1. I'm going to create a transfer function. First, we need denominator part. Denominator is convolution between a square plus 2 into zeta omega ns plus omega n square. And that term, along with that, we have another term Ts plus 1. So let us create a transfer function g equal to Tf of omega n square divided by our denominator term. If we see the step response of the system, we may get a response. Let it be that. See, let me put the value of t different and let us observe what happens. I am putting a huge value of t. Okay. Initially, when t equal to 1, you note that the system has settled within around 10 seconds. Now I am putting t is equal to 100. Okay, and this is a third order system in which one complex pole pair exists and it has some overshoot. Now let me create this system and let us see the step response. See, the system more or less look like that of a first order response. Actually, the system is a third order system in which there is a complex pole. That means there should be oscillation. But if you see the response, it has only first order kind of behavior. Why? Because if you put t equal to 100, the pole position will be minus 1 by 100, which is minus 0.01. And approximately it will take 400 seconds to settle. If I check the settling time, it will be around 391 seconds. Around 393 seconds. Okay. So approximately 4 times your time constant. That is 400 seconds it will take. But if you observe the second order pole, whatever we have considered, with zeta equal to 0.707 and omega 1 equal to 1, okay, zeta omega n is 0.707, 4 by zeta omega n, if you look, it will be less than 10 seconds. So when compared with 400 second, 10 second is very, very small. That means the effect of the second order pole would have been completed within 10 seconds itself. So the overall response is dominated by the first order pole only. Now, even though the system is a third order system, your response looks like a first order system because the first order pole is more dominant in the sense that is nearer to your origin in the left hand side. And the second order pole here is comparatively in a far away position. So therefore, the net response will be like that of a first order system. This idea is called dominant pole approximation. If you have such a kind of system, you can neglect the higher order poles, their second order pole, whatever we had, non-dominant poles, and you can work as if it is a first order system. It reduces complexity. Okay. So this particular task is this only. Now let us put T a different value. T I am putting at 0.01. That means this particular pole will have its effect only for around 4 seconds, 0.04 seconds. After that, it will die out. Okay. It is very faster pole. Now let us create the transfer function. And see the step response. Now you see you are getting underdamped response. Why? Because the value of t whatever we put is very, very small when compared with the response of the second order pole, and it becomes non-dominant. Okay. So this is the effect of dominant pole, and this dominant pole helps to reduce the order of the system. While doing the next experiments, that is while discussing about compensators, we will see that the compensator effectively tries to adjust only the dominant pole of the system, okay, rather than the non-dominant poles. This is also a limitation as well, but all analyses are based on this limitation. In some sense, it is an advantage because we reduce the order of system, but in many cases, it will also be a limitation. The last part of our experiment is to analyze the effect of forward path gain in the closed loop performance of the system. We assume that you have a third order system. In the experiment, I given first order, second order, etc. But let me directly tell for a third order. Assume that you have a third order system of this form, that is k divided by s into s plus 1, s plus 2. That is in denominator you have s cube, 3s square, 2s, 0. In root locus, while explaining the theory, this system would have been considered first. It's a very standard textbook example. In ZPK of G, you can see this. I'm going to consider the system 1 by s into s plus 1, s plus 2. Here, what I'm going to do is, for different values of k, that is in numerator, there exists a k. Initially, I assumed it as 1. For different values of k, we are going to find the closed loop response. With k equal to 1, let us find the closed loop transfer function. For that, there is a command called feedback. Feedback of g, 1. By default, negative feedback is considered. It will list the closed loop transfer function. And let us get the step response of the closed loop system. If you observe the closed loop system, you will get some response. Let it be that. Let me change the value of k and let us see what happens. Instead of 1, I am going to put 6. Our system will oscillate completely. I am calculating the feedback system and the response of the closed loop system. You can see that system completely oscillates. Why? Because the value of forward path gain affects the closed loop pole of the system. Okay. In fact, this effect is given by a plot called root locus. If you plot R locus of G, that is root locus of G, it will show a graph in which each and every point corresponds to a value of k. Root locus, by definition, is the path traced by the closed loop poles of the system when any one of the parameters loop parameter of the system varies. Usually for design, we consider k. Okay, so this graph is for k varying from 0 to infinity. Okay, actually, this will not be infinity, k varying from 0 to some high value, because infinity means you require infinite graph. Now, what happens is you can infer these behavior, that is, your closed loop pole positions from root locus. So what it says is at very low value of k, uh, the X symbol indicates the closed loop pole. They will be the right hand side. Whatever pole in the right hand side that is moved to, that will move towards left, and whatever pole at -1 that will move towards the right hand side. And what happens? The pole in the right hand side that will be more dominant, and because of that, the system will have over damped kind of behavior. Let me sketch the response for low value of k. Let k equal to 0.1. Get the closed loop response. Calculated GCL. If you find a closed loop response, it is more or less an over damped behavior. But if you increase the value of k, instead of 0.1, if I put 2, now you can see that the system becomes underdamped and it has some kind of sinusoidal damped oscillations. So what happens is because your pole position in closed loop is having some kind of imaginary part. Those information can be fetched from root locus. Okay. Now here you see for very low value of k, the poles will be on the real axis itself. That means there will be no oscillation. System will have damped kind of response. As k increases, at some point you will have critically damped response, and after that, imaginary part will vary. That will start to come. So once again, here what happens as k increases, imaginary part is also there. Along with that, pole is also moving towards the right hand side. Okay, so because of that, system speed will reduce, settling time will reduce, and at some point, for this particular problem at k equal to 6, your poles will be exactly on imaginary axis, and because of that, even though you have 3 poles, 2 pole will be on imaginary axis, other thing will be in the left hand side. That becomes non-dominant. The 2 poles on the imaginary axis will exhibit sustained oscillation. And if you increase the value of k even 0.1 beyond 6, then system will become unstable. Okay. This is the information that you can fetch from the root locus. Let me fetch the root locus for 6.1. Okay, for 6 it is sustained oscillation. We have seen it. Let us calculate for 6.1. Second, let me calculate feedback transfer function, closed loop transfer function, and then step response. See, system now becomes unstable. Here what happens? Let us zoom this graph. Think, there is no horizontal or vertical zoom. I think in offline MATLAB you will have such things. That's why I prefer our offline option. Online you can calculate anything, but user interface is little bit tricky. Okay, so if you zoom further, you can see that the response will be continuously oscillating. At the same time, it will be exponentially increasing. Let me calculate for some specific time period. from 0 to 1 second. Okay, we need to give time explicitly. Okay, let us calculate the response for first 100 seconds. Okay, 0 is to 1 is to 100. From 0th time for what equal to 1 second, 2 second, etc. See, this graph doesn't seem to be good. Why? Because the time duration is large. If we consider step size of 0.1 second, and here you can see there is a sinusoidal oscillation, but what happens is it is exponentially growing. So because of that, system becomes unstable. Why it is becoming unstable? Because for a high value of k, we have put the k value as 6.1. For 6, system is marginally stable. Even a very small value beyond that, your pole locations will be in the right hand side. Whenever I say pole in root locus, closed loop pole location, that will be in the right hand side. Because of that, your system will become unstable. So even without doing huge analysis, just to be looking into the root locus, it is possible to guess what will happen to the system response. That is why root locus is more popular. Okay. So whatever analysis you will be doing, that things I have demonstrated here. With this, let me stop my recording. It is enough.